Welcome. Last time we were talking about the vector character of angular momentum, angular quantities, and we used the right-hand rule to associate a direction with something that is rotating around. So you use the fingers of your right hand, curl those around in the direction of the rotation, and your thumb points in the direction the vector associated would point. In the case of a cross product, if you align your fingers first with the first vector and then rotate through an angle less than 180 degrees to get to the second one, your right thumb points in the direction of the cross product. So we saw that the torque is the cross product of the position vector from some chosen reference point to the point of application of the force, and the angular momentum is of a point particle is just r cross p. And we saw, remember, for the second time, that a point particle moving in a straight line does or doesn't have angular momentum. Depends on the reference point, but in general, it certainly can. Okay? So we started out, why do you think we started out with a definition of angular momentum that was only about rotating things around a fixed axis? Because it's easier. It's easier to visualize. You can imagine the kinds of collision experiments that you could do. But in general, angular quantities are defined as here, well, there. And so we're going to see today how to decompose the angular momentum quantities for an extended object, not just a point particle. And what we will discover is that the angular momentum can be composed of two different parts. The orbital part, like the Earth has by virtue of going round the sun, and a spin part, well, the Earth also has angular momentum associated with rotating about its axis. And the total angular momentum of a rigid body will then be the sum of orbital and spin angular momentum. But I wanted to offer a word of warning. Vector quantities require vector notation. This is still an important warning. So on the board, I'm going to use arrows over them, but in most printed work, boldface. Two vectors are equal only if they have the same magnitude and point in the same direction. So a statement that two quantities are the same, if you're not careful about whether you're writing the vector or the scalar, those statements can mean two very different things. And no, this is not random. The notation is really important. So if I have a particle moving around in this fashion around a circle, what's the direction of its angular momentum? Given the coordinate system that I put there. Is that positive z, negative z?
Negative z.
Negative z. So this is a good statement. L is r cross p. And we just worked that out. This, however, is not a good statement. What's wrong with that? Vectors equals vectors. That's good, right? Isn't that good? A little iffy, huh? What's not good about this? Yeah, the direction is totally wrong. The angular momentum, we argued, is in the negative z direction. V, on the other hand, is pointing in the, what, xy plane somewhere. Okay? So just because you can't just slap the vector sign on because you know I've harangued you that you can't have vectors equal scalars. Has to earn it. Has to actually make sense. Oh, come on. Where's my... yeah, that looks good. Yes. All right. So In this case, it would be in the negative z direction, m, and because it's going around a circle, b is already perpendicular to d, so the sine of the angle between them is just 1.